his. And it's fantastic to see so many in the audience, even if I see a few of you very small here on the screen. And we are hoping for more than 100 participants today. So the online format is fantastic in the way to broaden the distribution of an event like this. My name is Håkan Edlund. I'm professor in physical chemistry. I'm going to be the chair of today's thesis defense. So the main actors today is, of course, Olof Ferritsius, and together with the faculty opponent, Øyvind Veiby Gregersen. He's from NTNU, Norwegian University of Science and Technology in Trondheim, Norway. And Olof is today going to defend his thesis, and it's about what is beyond averages, some aspects of how to describe a heterogeneous material on a particular level, and Olof has focused on different mechanical pulps. The main supervisor has been Birgitta Engberg, and the co-supervisors have been Professor Per Engstrand and Dr. Mats Rundlöv. And at the thesis defense, we do also have an examining committee here today, consisting of 3 members. And the members of the committee is also the examiners of the doctoral thesis today. So the members are Urban Wiklund, professor in materials science at Uppsala University, Antti Happala, professor in wood material science at University of Eastern Finland in Joensuu. And last, the one who got out of bed extra early this morning, or his morning, Professor Mark Martinez from the University of British Columbia, Vancouver. He's like 9 hours away from us in some way. So the procedures of today's defense will be as follows. First, Olof will give a presentation that is a brief overview of his research, findings and conclusions in his thesis. And in that part, no questions are allowed from the audience. And the presentation will take a while, 55 minutes. And then after a short break, coffee break for 10 minutes, and when we are all gathered back, the opponent leads a scientific discussion with the respondent, asking critical questions about the respondent's work. Usually this part takes 45 minutes or up to an hour, but the opponent stops when he is satisfied. So the time there is, so the sky is the limit. After a satisfied opponent, I will invite the members of the examining committee to pose questions to the respondent. And finally, I will invite you, the rest of the audience, to ask questions to the respondent. At last, I will terminate this public part of the defense and gather the examining committee in another separate room digitally for the decision-making meeting where the committee decides whether the grade is approved or failed. And then after 20 to 30 minutes, the chairman of the examining committee will then be back here in this Zoom room in public and announce the decision. Okay, so let us start, and the floor is yours, Olof.
Thank you very much, Håkan. Good morning.
Okay, so we seem to have some technical issues with the sound. We'll fix it and be back shortly. Apologizes for the inconvenience.
Okay. Product. It's okay.
Now it seems to be working. Yes, Olof.
Okay, thank you. Here you see a product. It's a cross-section of a paper, could also be a board. And the raw material, that's something we need to make a product. Here you see the raw material we have in pulping. It's a cross-section of a log, and you see the earrings here with, it's a really heterogeneous material here, and you also see it's very heterogeneous in the product. But we need something more than raw material. We need processes. Here you see a schematic drawing of a refiner where we separate the finers, and we have a paper machine so we can make the product. And here we have the pulp. It's a microscope photo, and you see the cross section. So this pulp, you can see it's heterogeneous, and it's the product from this one. But on the other side here, you have the raw material, and it makes a product. So a certain material can be both raw material and a product. But we need something more than product, raw material, and a process. We need people to operate, to speak with each other. And they commonly agree that uniformity is very important. All you, I can't see, can they see up there? Yeah, okay, they see.
Yeah.
Good. You see, we use the same words, but sometimes it's hard to overlap. So we mean different things. So the purpose of this thesis is to show how can we get a more common language to speak with each other in this process. So we have this flow where we can put claims to have target values, so we can put it down to these operators and then can feed the material, and they get what they wish to get at the paper machine. Then we have another stream here commonly used. We can also take samples here and in the lab have dewatering, press, dry, and simulate a product, which we call hand sheet. But this is not the same as making this, although we make it from the same fibers. So to be more specific, the main objective of this study is to give a detailed description of this heterogeneous material, and it should be based on images. But we also have another objective, second objective, it's to visualize these descriptions. And that's in order to get a more profound understanding, achieve uniformity, and also more clear communication along the value chain. And we have done these studies in mills. Mill operation within normal conditions. We have been in the Stora Kvarnsveden, Stora Enso Skoghall, making publication paper, respectively board, and also some samples from Stora Enso Fors and Hylte. And more specifically, we have focused on these two first mills, where we have studied process conditions and process configuration. And in this mill in Skoghall, we have studied the raw material. And to be specific, outside the scope, what we've been dealing with, it's network of particles and also what we commonly call fines, the very fine material. So images, those have been achieved with a fiber analyzer, Fiber Lab. And here you see 6 examples of fibers we have taken photos of with this equipment, optical fiber analyzer. And we measure something called length, how long are the particles, how bent are they, but we also go deeper. And from this analyzer, we can get wall thickness, diameter of the particles, as well as something we call fibrillation, which will occur when we treat them in the refiners in the process. I will now just make a very short summary of the whole study. Why does it not? So it's page -1. It's the front page of the thesis. And here you can see measurements where we have measured length of the particles and how curled are they, if they are bent or not. And normally we measure about 10,000, 20,000, 30,000 particles, even more. But common practice within our industry is to just go by the average value. We calculate an average of all these tens of thousands of particles. And then we make another examples, and then we start to compare these averages. However, what we will end up with at the end of this presentation is it's so much information to extract from these scatter here, which is actually not scatter. So we can go deeper beyond the averages, and we can draw curl versus length. We have the long particles here, and here you can see the very curled particles here. And you can also see that on top of this, here you see a distribution of the particles here. And you can see the most curled particles, they are around here in the length interval 0.6, 0.8 millimeter. And you can also see that the most curled particles, you can have a heat temperature map on top of this. They are very fibrillated. So you see here we have a symbol of the particles here, the most curled particles. They are really fibrillated, and these very straight particles, they are not fibrillated. So to summarize, go beyond averages. There is so much information to be extracted, and then we can hopefully communicate. So what's common practice within the industry? How do we communicate? I went over at the IMPC, the mechanical pulping conferences from 1973 to 2018, counted about 5,000 figures and extracted how do we describe the material? And you can see commonly used freeness, tensile strength. It's a lot of those data. However, not much about product, wooden raw material, nor uniformity. It's very rare. And this way of describing is to ignore that it's a heterogeneous material. So in this thesis, we will look closer to something called independent common factors, as well as fiber dimensions and distributions. It's very rare, 3 to 4% only. So it's not common practice. I will discuss later on here. So length, how difficult could it be to measure a length? Let's get byta. All right, okay. Here you have a model of a fiber, and it actually looks like this. It's 100 times longer than it's wide, so it's a really narrow one. And it's not a problem to measure the length of this fiber. In this case, in a real fiber, it's about 3-4 millimeter long. However, the problem is if you have two fibers to calculate an average from. So if you have one very short particle, so if this, in this case, it's 50 centimeter long, and you have one other which is almost close to 0 centimeter long, then the average will of course be 25 centimeters. However, we make another example. We have a very little particle. It's actually a particle here, but we don't see it. So we calculate an average, and then we end up having, the average is 50 centimeter. We don't see it, but if you start to see this particle, then it's 25 centimeters. So just to calculate an average is not easy. So I will make an illustration now what the problem is. tror jag det är okej, va? Nej, jag tror det är okej, va? Kiva. Nej. So here we have a study we did in Skoghall with CTMP. Here you have the raw material. It's in one case it was 100% sawmill chips, and then it was 100% roundwood chips from different parts of the log, so the fibers are different. And then you had a mixture of these two. And then we took sample of the chips, we digested it so we could run it through the fiber analyzer. And then we also took samples after the refiner. This is in a picture of a refiner. And then we took these samples and we ran it into a fiber analyzer. And such fiber analyzers, they give an image like this. Here you have the fiber length. It's calculated, and here you have the relative frequency of the fibers. And then we can look here that the digested chips, the sawmill chips, this one, there are very many long particles here. And then the roundwood, they have much less. It's just according to the school book, much less. And if you look on the CTMP here, coming out of the refiner, you can also see it's, of course, much lower length, but it's more long fibers in the sawmill chips compared to the roundwood chips. So actually, they are longer. We feed it with longer. It's very high yield in this process. Out comes also a longer particle. If we feed it with shorter, it comes out shorter according to this one. So based on this, we can calculate an average. It looks like this. Here you have the fiber length of the digested chips, and here you have the fiber length of the CTMP. And in this case, we have calculated average fiber length arithmetic. Every particle has one vote, so to say. And then you can see it's a negative correlation. So the longer particles we have in the chips, the shorter will come out of the refiner. So it's, I mean, I agree, it's very strange. So another way is to put more weights to the longer fibers because they are also heavier. So here, then we have something very commonly used in our industry is length-weighted fiber length. And if we plot the same data, you can see it doesn't matter what we feed here in the digested chips. The fiber length out of refiner is constant. Although we know it's important what we feed, but these figures of calculating which we use in our industry and in academia, it's not fitting to what we really see. So then it's a possibility to put even more length weight to the longer particles. That's something called length-weighted fiber length. And then we have here, based on the same data, digested chips fiber length versus on the CTMP. And then you can see it's something we get out what corresponds what we really measure in according to the distributions you just saw. So longer particles, as in the sawmill, in the feed, out will longer particles come. And of course, you can dig deeper into this data. It's a really fascinating word. So we can look at the R-square values here. Here it's almost 0.95. So we can draw a graph like this. Here you have what weight you put to the longer fibers, and here you have the R-square value. And you can see in the beginning, we have a rather good correlation. However, it's negative correlation. Here where we operate, common practice, as I mentioned, the length-weighted, operated by about 97% of in the publications I went through. So it's no correlation between what we feed to the refiner and what we get out. However, just close to that, you can see here we get a good correlation, a strong correlation. However, it's just 3% using this way of calculating it. So it's, again, common practice. We could question that, but put more weights and we can even go even a little bit higher. So then something else I showed, just independent common factors. What's that? It's a mathematical way of reduce the number of variables we are looking at. So it's inspired by Bill Strand of this way of working. We started in the Kvarnsveden mill in the late 80s. And just very short, the principle is you measure something on the pulp suspension, you measure you make hand sheets, and you measure strength and other stuff. But it's not necessary. You can reduce these variables to two independent common factors and give a name like reflecting something with fiber bonding and also how long are the fibers. If you wish to go for a third factor, then it should be size. But it's so important, they are independent. It took about a decade to understand the benefit of that. So we will focus on fiber bonding first. And just having two figures here, it's so easy. You can plot them versus each other. Fiber bonding versus long fiber influence. We were operating according to freeness, the traditional way within the industry for almost a century now to use that. And you can see it's not uniform, the quality, but you can specify a window. And what happened in Kvarnsveden, and I mean, that's some reason that we're standing here today. It was driven from the product side because there were problems with the product quality of the paper. We couldn't find any strange thing with freeness. However, this fiber bonding phenomena correlated strongly to the paper quality, the end product quality. So we managed, we said, don't go by freeness, just try to control F1 and F2 using the same window. And you see it was possible, data for half a year here. And they were more happy on the paper machine as well. So although we couldn't directly measure it, we could get figures on it and we could start to communicate along the chain. Chips, pulp, paper. And then when you try to learn a new language, you may do it very simple first, try to get the idea. So we did something like this. We took a stone ground pulp and a TMP, and we mixed them in different proportions from 0 to 100%. And just it was additive. They followed a straight line here. So that was encouraged. Then we thought if its mixer will fit, we went out, we took samples around the screen and a cleaner. The same fiber bonding versus long fiber influence. You can see the way they separated. Here you have the feed, here you have the reject, and here you have the accepts. Its screens separates according to fiber dimensions. However, the clean it's separated according to more specific service. And the different actions of these two equipment could clearly be seen here. Now, a process, very simple. Although it's not that very simple. Here you have a refiner, and then you have a whole bunch of equipment, and out comes a pulp. And that's what we normally use in the mill and discuss, and then we put on a table. But you can actually describe this whole process in a single map here. So we can discuss where are we. And for instance, we start the process here, and all this, not fooling around, but pumping around, treating it, mixing, remixing, ends up that you just take this step. As good as just, it's not necessary to separate like this. You can go straight on, and you can see it's so important where you start. So one conclusion is starting point is very important, and do it simple and just continue, and then you can discuss something around the quality. All this has been about not distributions, mainly. So now we have another example. Now it's going to be Yep. So we take a bigger fiber now. This is a very stiff fiber. You saw the very thick walled fibers, very strong. However, if you take the same length, you can also have this fiber. So that's actually what we have in our process. We have very stiff fibers, we have very flexible fibers. That's why we have gear rings in a log, you can see. But that we have ignored more or less completely in our industry. So we treat it as average, these two, although they are very different. So we can see how could we illustrate this distribution in properties. No. Run.
No,
Vi brukar se lilla bild. Ja.
okej. Vi ser inte.
Det var inte lilla bilden här.
Vi ser inte rättvisningsfil, men du kanske kan köra. Det var rättvisningsfil här. Och den, precis. Nu.
So, referring to this, we try to develop a method to get the distribution in bonding of the particles to reflect their heterogeneity. So we took many pulps from different sources, different grades. We separated in hydrocyclones to get streams with different bonding level. Here you can see photos of the different fibers. This is the very most developed fibers, and here I have chives and more thick-walled fibers. And we even focused on separating a bar magnet according to size. So actually, we are dealing with fibers in the area from 16 to 50 mesh in size. So many, we split a single fiber in many parts. And then we went with the factor analysis. We made the pulp suspension. We measure width, wall thickness, and external fibrillation. We make handshakes of these fractions measured and could combine them into a common bonding factor, reflecting about 70% of all the variations. And then when we have done this, then we apply this equation to every single fiber we have been measuring. And then we could get the distribution. Looked like this. Here I have the bind. Here you have the very stiff particles. You saw the thick-walled fibers. And here I have fibrillated collapsible fibers. And on this axis, you have the relative frequency. And then we have deal with single disc refiners and double disc refiners. And you can see the dotted lines here. They are very close to the primary, to the final pulp. So it's just on the final pulp, it's a little bit more energy added in the process. But even more interesting is that you can see they are different here. The single disc refiners and double disc refiner, that gives another different character of a pulp. And it has been known earlier, but it's also illustrated in these distributions. So it's a way to illustrate the distribution. And you can see the pattern from the primary stage. It's very much maintained until you go to the final pulp. So you can see they are close to each other. So the primary stage, so important. And you can also look like this. Here we have the double disc refiners. We have the primary pulp, a news grade, and even more NAD in the SE grade here. You can see how you switch the distribution to the higher side, more developed fibers, fibrils, and so on. And what you can do with the distributions, you can look on the tails of the distributions. Here you can go for the 5th percentile. You can see what happened here when you go to the 95th percentile, and see they are different. And even digging deeper into this, you can illustrate which fibers are treated. So here you have specific NAD in those, and here you have the 5th percentile, this, so to say, stiff end of the distributions. It's rather flat. You can treat, you can add NAD, but it's not so much influencing the fibers. However, this percentile, you can see it's increased the level more. So it's easier to refine. So it's really hard to get hold of those fibers at the more stiff end, more thick wall fibers. So that means, in summary, the more you treat the material, the more heterogeneous it will be. So we were inspired by this. So we also dissolved paper. We took paper from the paper machine, dissolved it in water, and then run through analyze. So you can see it just the character. It's there. The product is, of course, influenced by the raw material, the pulp. So we even looked what are others doing. So we ordered a newspaper from the Sundsvalls Tidning here, operating from Ortviken, and then we compared that with the double disc from Kvarnsveden, bind versus relative frequency. You can see the fingerprint, it's exactly the same. So it's so important. You can even go to get the information from the newspaper and see how it works. And we also ordered a paper from the Hallstavik mill here. And you can see it fitted very good with the single disc refiners in Kvarnsveden. You can even see here, it's a little bit difference here in that tail. We don't know the reason for that, but it's something you can get deeper going to these distributions, going beyond averages. Raw material, just a few words on that, because it could also fit to the chemical pulping here. We normally may wish to have rather much water in the chips. They shouldn't be too dry. So then we take maybe 1,000, 2,000 pieces of chips and we analyze it and get the average moisture or dryness content. So could we also go deeper behind averages here? So I took out 40 chips of the sawmill chips and 40 chips on the roundwood chips, measured moisture, dryness content of each individual particle. And you can see the averages are rather close to each other. However, if you look on the distribution, the roundwood chips have much more of the very dry chips. So it's also worth, along the whole process change, go behind averages. You may find something that will influence it. Just having the same average doesn't mean that you have the same quality or properties. So then we also run with the Skoghall mill, the CTMP, this trial with different proportions of different chips. We went like this, and then we got the bind distribution versus frequency. And you can see when we varied here, the different graphs here are different energy input in the refiner here, but it doesn't matter much. It's so much more important what we feed to the refiner than how we operate it. And you can see the bind distribution here differs, and it corresponds to what we have been seeing in the mill. So the raw material, again, pay attention to that and look how it really is. Energy efficiency is a very important area to work with. However, there is no common equation or rule or definition of energy efficiency. What we do is we feed something to refiner, add a lot of electrical energy, and then we get the product out. So we would, as low as possible of energy and as much to happen in the refiner as possible. And then actually we can use these distributions to calculate what will happen in and out. And then I will take the first example is you can see the primary pulp here, and then you have with the newsgrade here, these two, they are rather close to each other. But then you can calculate that have a big common area here to cover, but they are a little bit different. So you can use this distribution, the common area, to calculate energy efficiency. It's just a proposal, but you can go 1 minus common area and divided with specific energy. So then you can use this. And of course, if they have the same common area, then they are identical and there is no energy efficiency. So then you can go for the material in feed and material out. Primary stage, so the common area is 0.96, and then you can calculate the value of energy efficiency. You can do the same for the newsgrade TMP going to SC grade TMP. These two graphs here, it's a lower common area. However, there is much more energy added, so it will be a lower energy efficiency. And what you can do, you can even go to the material of the feed with the chips. You digest it, you digest the material out, the CTMP, you can calculate a common area of the primary refiner stage. And then you can see it's much more energy efficient in the beginning. So also this indicates focus on the beginning of the process. Wall thickness. That's something we often speak about. A short examples here, what you can be seen. We have the sawmill chips and we run roundwood chips into the refiner. Out comes pulp, sawmill based and roundwood based. And normally these fibers are more thick-walled in the sawmill. That's from the outer part of the log. And in this case, we took samples, we made lab hand sheets and measured something, the strength, tensile index, and it was, in this case, much higher compared to the roundwood. And maybe it's a little bit to wonder, but they are more thick-walled, so why are they bonding better? So then we took the digester here, so we could dissolve the fibers, run it through the fiber analyzer, and then we run the fiber analyzer here. So we got this then. Here you have the wall thickness. Here you have the digested chips, and here you have the CTMP. And you can see that there are more thick-walled fibers in the chips, in the sawmill chips. But surprisingly, the ranking is the other way around in the process here. You can see they are more thick-walled out in the pulp. And that's the problem here, that because normally these analyzers give an average where you include all particles, even those very close to 0 millimeter long. If you just skip those and go by the length interval in the distribution, you can cut that and 1 to 6 millimeter, and then you can see, okay, this remains, and here you can see, okay, then it's the same ranking anyhow. You have longer, more thick-walled fibers here, and you have more thick walls in the pulp, so that fits. But the problem is then you get higher fiber length because here you have the CTMP and here you have the digested. So what we did then we digested also the CTMP and run it through the fiber analyzer. And then you get this ranking. You can see, okay, shorter, more thin-walled in, that corresponds to what you have here. And you can even look here. With this one, you lose, you go down in wall thickness by 2 micrometer, whereas it's much less difference here in delta, -1 micrometer. So you do much more. You treat the fiber wall, you get more fibrils, and then you get a better understanding what happens in the refiner. So you can look from hand sheets, you go back to measure here what comes out, but to understand what happens here, you must also measure what goes in. So the whole chain, it should fit together. So the conclusion is we need the feed, even the feed to the feed, to get a deeper understanding. What are we doing in this process? Then another possibility with these distributions, you can also cut it according to length. And this is an example here. You can see the length of the particles and the wall of these different slices. We slice the whole thing here. And you can see the most thick-walled fibers are those in the sawmill here, along the whole chain here. And the most thin-walled are the roundwood chips. So you can even understand, okay, they are really more thick-walled, but they are also treated more. Furthermore, what you can see, which is impossible with averages, is you have a dip here. We just happen to see it. We don't understand why is it like that. But then we thought, okay, if we go and cut the wood into early wood and summer wood particles, late wood, those are the thick-walled fibers. And the early wood, those are the thin-walled fibers, and then the natural mixture here. And you can see we dissolved it and run it through the analyzer. And even in the raw material, you have this characteristic dip, which I have no idea why is it like that. That's ongoing studies on that. So the final illustration now, we started with measuring fiber length. So the last one now. So how difficult could it be to measure a length? If the fibers are very straight, then it's not a problem. But if they turn to be very curled, it's really hard. I mean, this fiber, how do we measure the length of that? It seems to be short, although it's very long. So that's a problem. We actually don't measure fiber length. We take photos and then we measure the fiber length. So. Yep. Thank you. Yeah, curved. Just to give an idea what that is. It's how curved the fibers are. So in the analyzer, we measure the length along the particle and the straight distance. And you can see the curl of the C is 73%, it's 86 for U, it's more straight here. And for the very straight particles, it's 0. And you have a huge variation here. So to understand more, how does curl influence fiber length? Then we did the simulation. We built a simple fiber, 3 sections here, and then it could be turned here, and then it could also rotate to simulate it. And then we expanded it to make 21 sections. And then we run it through like this. Here you have length versus curl, and all these fibers here are of the length of 1 millimeter. And then we simulate, as I said, they could be more bent, they could be more curled. So you see, although all are 1 millimeter, if they are very curled, the data, the analyzer detects this as being shorter. So we, by going by the photos, we were actually drawing the wrong conclusion what happens with the fiber. And sometimes it could be a process that they get more curled, but they get longer at the same time and having the same average fiber length, although just as a number, but they could be very curled and looking different. So you can see here they could be, if they are looking very straight here, they are just much shorter, and if it happens to be taking photo from 90 degrees, much longer. So just measuring something like length is not easy. And here we have 16 photos in the simulation, photos of particles. The low bendability, 16 random fibers, they look very much the same. But if you treat them more, so you get a higher possibility to be bent, to take 16 random fibers here, they could look very different. So again, we see the more we treat the particles, the more heterogeneous will the whole material be. So to wrap it up here, where we started, we had the summary on the front page of the thesis. We had length and the curl. We had measure of 10, 20, 30, 50, 60,000 fibers. Although we measure that, we just calculate an average. And then we do the same with another pulp, and then we try to compare averages to understand how is curl influenced by something, how is length influenced it. But we can do as we did earlier. We can slice this one and look at the long particles. Which particles are most curled? Then we slice like this into length sections, and then we plotted it versus curl, average curl in each length section. And then you can see the conclusion we can draw then is the longest particle are the most curled. And then you see it goes down, and here you have also around 1 millimeter, you have a little bit local maximum in curl. However, this is not correct. So what we did then, we also sliced it into curl to make a graph like this, where we have length versus curl, and then the numbers here in each square, it shows how many particles do we have in each square here. So you can, and then if we skip those having very few particles, then you can see here we get another picture. The most curl particles are those around 0.8 millimeter. No. Those are the most curled. And that seem to be very curled of the long particles is that you have no very straight particles. So the average will show that it's much longer curl particles of the longest one. But that's an erroneous conclusion. So the most curl are these particles, although most of these particles are very straight. So dealing with averages, which is based on wide and skewed distributions, will give the wrong information. So, and a last step here, we can see why are those most curled, these particles. So then we could add, instead of these 3 dimensions, we can have a 4th dimensions. We have the same graph here, but on top of that, we added the degree of fibrillation for each square, average fibrillation in each square. So these are the most fibrillated particles, and they have been treated more, we can assume, and that's why they are curled. But those particles down here, which have the same length, but very straight, they have no much fibrillation. So just going behind the average here, maybe here we have, in summary, we work with about 3, 4, 5,000 values, while we just have 3 values here. So we must go beyond averages just to understand the material. Just one slide showing chemical pulp. It's more or less the same here. You can go working with those properties you get from analyzers and see here that the most long particles are here. And then just something, if you remember the dip, it can also be visible here. Here you have an area with a little bit more thin-walled particles. So you can also use this one to extract subsamples, and then you can compare wall to curl. You can see it goes in that direction, but even closer calculation to curl correlation, you go by fibrillation. So behind that single average, you can make a lot of subsamples. And you can even extract what Forgax did in 1963, SNL, based on a single sample. To summarize, ABC, what have we learned? We have learned that no good averages. B, we must look at the data. We must look at the material, taking photos, look at it, as also Forgax did when he developed his system. And when we have looked at it, we can characterize it, describe it. Here you have the distribution, but if you look, these steps are the averages here. They are very close. You must go beyond that. You can even make those graphs here. Try to understand why is it as it is, and try to understand how is it. And what we can do then is, to summarize, wood, the raw material, extremely important, known before, but even more you must go and take those samples before a step. Primary stage, very important. Independent factors, I mean, strongly realize that then you can even go and try to optimize the system because they are really independent. You can play them. And stand-ups and common practice. Put questions. Be convinced that you're working with the right data and not as it has been tradition. And in every mill I've been to, they speak uniformity is so important. Just in a single mill, we have developed a system where we can trend uniformity and speak about it. And the last point here, what I realized using this PhD study, you may be able to ask more pertinent questions to work with the right stuff. Thank you very much for your kind attention.
Thank you, Olof, for a very illustrative